Einstein's departure. Since Einstein has cut loose from the ether, he lacks this canvas, and therewith, at the first glance, also loses the possibility of fixing the positions of the heavenly bodies and mathematically describing their movement, that is, by giving comparisons that define the positions at every moment. How Einstein has overcome this difficulty may be somewhat elucidated through a simple illustration. On the surface of the Earth, the attraction of gravitation causes all bodies to fall along vertical lines. And indeed, when one omits the resistance of the air with an equally accelerated movement, the velocity increases in equal degrees in equal consecutive divisions of time at a rate that, in this country, gives the velocity attained at the end of a second as 981 centimeters, 32.2 feet, per second. The number 981 defines the acceleration in the field of gravitation, and this field is fully characterized by that single number. With its help, we can also calculate the movement of an object hurled out in an arbitrary direction. In order to measure the acceleration, we let the body drop alongside of a vertical measure set solidly on the ground. On this scale, we read at every moment the figure that indicates the height, the only coordinate that is of importance in this rectilinear movement. Now we ask, what would we be able to see if the measure were not bound solidly to the Earth? If it, let us suppose, moved down or up with the place where it is located and where we are ourselves. If in this case the speed were constant, then, and this is in accord with the special theory of relativity, there would be no motion observed at all. We should again find an acceleration of 981 for a falling body. It would be different if the measure moved with changeable velocity. If it went down with a constant acceleration of 981 itself, then an object could remain permanently at the same point on the measure, or could move up or down itself alongside of it with constant speed. The relative movement of the body with regard to the measure should be without acceleration, and if we had to judge only by what we observed in the spot where we were and which was falling itself, then we should get the impression that there was no gravitation at all. If the measure goes down with an acceleration equal to a half or a third of what it just was, then the relative motion of the body will, of course, be accelerated, but we should find the increase in velocity per second 1/2 or 2/3 of 981. If, finally, we let the measure rise with a uniformly accelerated movement, then we shall find a greater acceleration than 981 for the body itself. Thus we see that we, also when the measure is not attached to the Earth, disregarding its displacement, may describe the motion of the body in respect to the measure always in the same way, that is, as one uniformly accelerated, as we ascribe now and again a fixed value to the acceleration of the sphere of gravitation, in a particular case the value of 0. Of course, in the case here under consideration, the use of a measure fixed immovably upon the Earth should merit all recommendation. But in the spaces of the solar system we have, now that we have abandoned the ether, no such support. We can no longer establish a system of coordinates, like the one just mentioned, in a universal intermediate matter, and if we were to arrive in one way or another at a definite system of lines crossing each other in 3 directions, then we should be able to use just as well another similar system that in respect to the first moves this or that way. we should also be able to remodel the system of coordinates in all kinds of ways, for example by extension or compression. That in all these cases for fixed bodies that do not participate in the movement or the remodeling of the system, other coordinates will be read off again and again is clear.